Alright, you can start off this lesson by dilating segments AC and AB from center A and using a scale factor of 3. It's difficult for me to do that on the iPad, of course, but you can do that using your compass and a straight edge. But if you were, I'll just kind of pretend to do this. You would extend AC. Whoops, let me get my line here. You would extend AC, and you would extend AB. You would use a straight edge, and then you would take your compass. If I want a scale factor of 3, you would mark off where AC is, and then you would mark off that distance 2 more times, so you have 3 of them. Same thing with AB. You would mark off that distance 2 more times. Here's C prime, here's B prime, and B maps to D, so actually I wouldn't label it with primes. I would label the new guy. B maps to D, C maps to E, and then you would connect that and compare that to the first one. Would triangle ABC be similar to ADE? Well, that answer would be yes, because we know that when we map lines like BC is going to be parallel to DE, which means we have corresponding angles are congruent. So we know angle A is congruent to angle A, and then we could choose another pair, and we know they are congruent. So we have angle-angle similarity. Angle 1 is also congruent to angle 2. Okay, well, what we actually did here is we created those 2 angles, but we actually started with an angle, and we created 2 sides that were in proportion. And we showed that if you start with 2 sides and the included angle, you can get to similar triangles, just like you could if you started with 2 angles. So that's our first theorem here. 2 triangles are similar if they have one pair of corresponding angles that are congruent and the sides that create that angle are proportional. And that is side angle side similarity. It's not congruence, it's similarity. So in the case that we just did, we would say angle A is congruent to angle A, and AB over AD is going to be equal to AC over AE. So the ratios are going to be the same. The side lengths, no, but the ratios that they create are going to be the same, and that's side angle side similarity. So now we're going to demonstrate the last similarity theorem. If we look at this figure and answer the questions to determine whether or not the triangles are similar. Well, what information is given about that figure? And if you look, we don't have any information on the angles, but we just have all the side lengths. And that's it. Well, if we compare the corresponding side lengths, let's see what happens. If we take the 7, which is BC, that's going to correspond to the 3.5, and that's a ratio of 2. The 2.82 is going to correspond to the 1.41, that's also a ratio of 2. And the 5.4 corresponds to the 2.7, and that's also a ratio of 2. So all sides are proportional when we do that. And that's going to lead to our final similarity criterion, which is this: the side-side-side criterion for 2 triangles to be similar. 2 triangles are similar if their corresponding sides are proportional. So all 3 pairs of corresponding sides have to have the same proportion. So you have to check all 3 pairs. And if they are, then you have side-side-side similarity. So if I have triangle ABC and DEF, I don't have to know anything about the angles. If I can show that AB, let's just say over DE, corresponding sides, if that ratio is equal to AC over DF, which is equal to BC over EF, then we have side-side-side similarity, and we can prove the triangles are similar. So we're going to work through 3 examples in our notes, and then you'll do the rest in class. For these, we want to know if they're going to be similar or not, and we have our 3 similarity criteria we could use, either angle-angle, side-angle-side, or side-side-side. If we look at the first image, you'll see that only the side lengths are given. So we're going to have to show this by side, side, side. And we got to make sure we get our correspondences correct. So triangle ABC, if you look at the angle measures, ABC has got to correspond with FED, because this is the longest side for the small one, and this is the longest side for the big triangle. And then we're going to set up some ratios. So if I want to figure out, if I look at the smallest sides, I can look at EF over AB, and that's going to be 0.68 over 1. So that has a ratio of 0.68. Well, then we can look at ED, the longest sides, ED over BC. And if I do that, that's 2.42 over 6.4. Well, here's what happens. 2.42 over 6.4, that's only 0.378, so we can stop right there. We don't have the same ratio between corresponding sides, so this is a no. The triangles are not similar because the sides are not proportional. They look similar, but you really have to go through the math to prove it. So we can't use any similarity correspondence. So let's look at the second one. We have triangle ABC and triangle DEF, and that's how I'm going to write it. Triangle ABC would correspond to triangle DEF. So if we look at this guy, we have one angle, and then we have the two sides. So we're going to try to show this with side angle side similarity. The angles are good. They're congruent. So let's just look at the ratio of the sides. If we take AB over DE, AB over DE, AB is 3, DE is 1.5. That's a ratio of 2. So now we need to take CB over FE, and that's 3.13 over 1.565, and that also comes up to 2. So this is a yes by side angle side similarity. Two sides and the included angle. The sides are in proportion and the angles are congruent. So our last example is probably our easiest. Are the triangles shown below similar? If we look at this guy, all we are given are these angle measurements. So we have one pair of congruent angles, but they also share an angle up here, so that's reflexive. We could say angle A is congruent to angle A because that's reflexive if you look at the two triangles. So we do know that triangle ABC is going to be similar to triangle ADE, and that's by angle-angle similarity. So those are the three similarity criteria that we are going to work on some more in class.